episode 5, we were discussing some constructions and concepts required to solve the membership problem for pedigree polytopes. We discussed folding X so that we could recursively define a layered network for each K and how solving certain problems in that network, mainly some flow problems, will help in providing results connecting membership and pedigree polytope and the solution to a multi-commodity flow problem defined for K. So uh, we were in this process. So here we will first consider, as promised, a simple example to explain the first stage, or when K equal to 4, the network that is formed. And as mentioned earlier, only when this network has a feasible solution, then we go into the next stage. So we'll consider a few examples before we move on to describe other details of this approach. In general, it may not be easy to find the nk-rk mu that is constructed after we know F4 is feasible. In this problem that we were discussing, we have already identified the rigid arcs and we know the flow along the z-dock. So the problem has been simple in that case, but in general it may not be like that. So we need the frozen flow finding algorithm. Before we describe the algorithm, we will go through some of the definitions, and once we understand the definitions, we can go through the steps in the frozen flow finding algorithm. Here we consider another example, and in this case the finding strongly connected component is not that easy, but it's still easy. But in general we may use certain algorithms to find the strongly connected component, which we'll see soon. Finding strongly connected components in this graph is easy. Notice that the destination node 2, 4 has only arcs going out of that node. Hence, this is a strongly connected component by itself. And also notice 1, 3 has connections to 1, 2, 2, 3, and 3, 4 by edges. This means this group of nodes form a strongly connected component. That means you can go from any node in this group to any other node and come back. That is like, for instance, you can go to 1, 3, 1, 2, then come back to 1, 3, and then go to 2, 3, come back, and then go to 3, 4, and come back to 1, 3. That way, all the nodes in this are in a strongly connected component. Next, notice that origin node 1, 2 has an arc going out to the strongly connected component 2 and an arc coming from strongly connected component 1. And thus, this 1, 2, origin node 1, 2 is a component, the strongly connected component by itself. Similarly, the origin node 2, 3 is a strongly connected component by itself. Thus, we have 4 strongly connected components. Next, we find the set of interfaces and the set of bridges in graph GF. Recollect the definition of an interface between two strongly connected components. If you have an arc, that is called an interface. Thus, we can see 1, 2, 2, 3, 2, 3, 1, 2, 2, 3, 3, 4. These are interfaces between two strongly connected components. In addition, you have 2, 4 and 1, 2. They have an arc, so that is a interface. And 2, 4, 2, 3 is an arc, that's an interface. Similarly, we can find the set of bridges, and from the definition of the set of bridges, each strongly connected component is considered as a graph, and within that, if you remove any edge, it should have more components. That's how the bridges are defined. So since 3 of the 4 strongly connected components have only a single vertex, these have no bridges. But the component 2 has 4 nodes, and they are all connected by edges. So any removal of any edge in this component makes more components. So each one of those edges, that is 1, 3 to 1, 2, 1, 3 to 2, 3, and 1, 3 to 3, 4, they're all bridges. Thus, we have found the rigid pedigrees in this example. So we have pedigrees P1, P2, P3, P4, and P5 as shown in this slide. So each of them is a pedigree in P5, that is the set of pedigrees for n equal to 5. Our next task is to construct the layered network for k greater than 4, that in our case it should be k equal to 5. And we should use certain simplifying notations, because you would have noticed we were referring to the nodes in our FAT problem corresponding to k equal to 4 with 4 and the edge, 5 and the edge, etc. So instead we would use the notation given here. Here we go through the steps involved in checking membership of a given X that belongs to PMIN, whether it is in the pedigree polytope. So the first step is to check that X is in PMIN. If it doesn't belong to that, that means if it's not feasible for the MI formulation, then that X cannot be in convex PN. So we go to the next step of constructing F4 for k equal to 4. And if F4 is feasible, then we go further, otherwise we stop. So we saw some examples for constructing F4. And once that is feasible, we go for constructing N4 R4 mu. And either N4 or R4 could be empty, but not both. And once that has been done, if k equal to 4, that means if n is k equal to 4, of course, the first run through, then we increase k to k plus 1, check whether k is less than n. If k equal to n, we can stop, and we have the conclusion. Otherwise, we know that X belongs to convex PK, and we construct Fk, check whether Fk is feasible. If not, we stop. Otherwise, then we go ahead and construct nk or k mu, and we need to do something more, that is we find a multi-commodity problem and check whether that problem is feasible. If it is feasible, we say the problem is well defined, otherwise we stop. Then we increase k and continue. This is how we go through checking membership in pedigree polytope. We need to justify each of these steps is valid and our conclusions will be correct.